very helpful. In the future, if you can, I'll definitely try to remember to record it. But if for some reason it's not recorded, definitely let me know, because this is going to help those students who cannot be here today. So now it's recorded. Excellent. So, well, they can read it. It's right there. Let's see. Conversational functions. Let's see. Suppose we're given f of x equals x squared minus x, h of x equals 3x minus 2. Now, compositional functions, basically we take two functions to make a new function out of them. Or maybe we take multiple functions and create a new function. And the way we create a new function is we take one function, we substitute that function into a second function by replacing all the x's. So the notation for composition of functions either going to be f with, let's say we talk about f and h here, so it will be f composed with h, so f with a little circle, h, and then x is just an input. So that's one notation. You can write this as f of, with the parentheses, h of x. So putting the h of x inside the function f of x, but where the x should be. So both are equivalent. So this is the f of h, and it's the same thing, f of h, right here. So what that means is that the h is going to be the sort of like the expression to replace x. So the h of x goes into f of x. And if we want to find it, it's going to be, we literally just take the h of x as the expression, 3x minus 2. And we're going to take 3x minus 2, we're going to put into this f of x by replacing all the x's in there. So there's the x in the x squared, there's the x being subtracted, so we're going to put in there. So it becomes the x squared becomes 3x minus 2 squared. We literally replace the x with 3x minus 2. And then minus the x, the second x becomes minus 3x minus 2. So that will become, just simplifying, so that's going to be 3x minus 2 squared. If we don't know, we can do it on the side by foiling. So that's going to be 3x times 3x, that's a 9x squared. 3x times -2 minus 6x. -2 times 3x, that's minus 6x again. -2 minus 2 become positive 4. So that's coming from the first part. And then we have to distribute the negative into the second parentheses. So that's going to be minus 3x plus 2. And now if we simplify every term by combining like terms, so we get 9x squared, then we have minus 6x minus 6x minus 3x minus 15x plus 4 plus 2 plus 6. So that's the function that we made out of f and h. That's the f of h function. We could also find h of f of x by taking f of x, put it into h of x. That's often they will trick you by asking you to find, let's see, f of x. So what this says is that, okay, so I'm going to take the function f of x, I'm going to put into itself to replace all the x's. So what that means is that, so recall that f of x equals x squared minus x. That's what f of x is, right? So what this one says, the f of x, which says we're going to take this expression, x squared minus x, we're going to put into itself to replace this first x and to replace this x. So this is the f of x, which is f of x was x squared minus x. So I'm going to use parentheses there. And inside the parentheses, I'm going to put where f of x was, which is x squared minus x squared minus x. So f of x itself being put into the function f of x. And just replacing x. And again, we can expand it. So if we FOIL the first part, I'm not going to do the work. Hopefully that's okay. So that's going to be x squared. I should do this. X squared minus x squared. So that's x squared minus x times x squared minus x. So that's going to be x squared. That's x to the fourth power. X squared times x, that's minus x cubed. Minus x squared, that's minus x cubed. And minus x, so that's a positive x squared. And outside we have a subtraction, so we need to distribute the negative. So it becomes minus x squared plus x. And if we simplify this, so we get x to the fourth minus 2x cubed. The 2x squares give us a 0 because one is positive, one is negative, plus x at the end. Any questions on this? But often, we don't need the function. We probably want to evaluate the compositional function at a given x value. So that will involving finding, for example, let's see, h of f, the composition of h of f at, let's see, x equals 2, right? So another notation for this is h parentheses f parentheses 2, close the two parentheses. So what we do is we're going to take 2, we're going to put into the f function first, because 2 is the input of the f function. And then whatever we end up with, we're going to put into the h function. So note, the first thing we're going to find is f of 2, which is taking 2 put into the f function. So f has x squared minus x. So, but instead of having x there, we're going to put 2 inside. So we get 2 squared, 4 minus 2, which is 2, right? And then that's f of 2. And we're going to take f of 2. We're going to put into the h function. So h of f of 2 becomes h of 2 now, because of the f of 2 is equal to 2. So h of 2, we're going to take 2, put it in the h function, which is 3x minus 2. So that's a 3 times some parentheses minus 2. The parentheses has a value of 2, because it must be the same value. So that's 6 minus 2, 4. So this is how we find the compositional function evaluated at a given x value. Now we can also look at a table of, if we don't know the actual function, let's see, we have a table of values. Let's see, this is x values equals 1, 2, 3, 4, and then we have f of x equals, let's see, 6, 7, 8, 9. Then we have g of x equals 1, 3, 5, 7, for example, right? So those are the values given. So what we can do is we can practice the same thing, finding f of g at, let's see, x equals 3. Mm, 5, 10, sorry, I'm adding another column here, 5, 10, 9. Okay, so what this notation says, I'm going to find f of g of 3. So the first thing we need is the inner part, g of 3. So g of 3 from the table, say, okay, x equals 3, what is the g function? Give me that, give me a 5. So g of 3 equals 5. And this 5 is going to go into the parentheses to replace g of 3. So this becomes f of, instead of g of 3, we're going to put 5 there. Now we need to find f of 5 using the table. So x equals 5, f of x equals 10. So that's the final answer. F of g of 3 equals 10. Sometimes they might give you two graphs where you can actually look at the x value, try to find the y value, which I'm not going to do here. For example, it might say, okay, f of x looks like this, and the g of x probably looks like this. Okay, so what is f of g of 2, right? Then you're just going to find the corresponding function, use the input to find the y, take the y, treat it as the x in the second function to find the y. All right, any questions on this so far? All right, so related to conversational functions, sometimes they ask you to find expression, like I'm still using the same example. So recall f of x equals x squared minus x, h of x equals 3x minus 2. That's what we had. Let's see, they might ask you to find, okay, what is f minus 2h of x? So this is not conversational functions, but it's just function algebra, right? Algebraic calculations of with functions. So what we do here is we just follow whatever the expression given. So it says f minus 2h. So we're going to take x squared minus x. That's where f is. So we're going to put it here. X squared minus x. And then we're going to subtract 2 times h of x. And h of x, we know it's going to be 3x minus 2. So 3x minus 2 goes in there. And the rest is about simplifying. So we have x squared minus x minus, distribute the -2, so minus 6x. And -2 become positive 4. And we just have to simplify everything. So we get x squared minus 7x plus 4. So that will be the function given by f minus 2h. Okay. Another problem related to this could be multiplication. For example, they might say, okay, find f times h of x, or even change the problem, f times h of 3. So what that means is that, okay, so we need to find the product first, and then we're going to put 3 in there. So that's going to be x squared minus x times 3x minus 2. But then we're going to evaluate this expression at x equals 3. Now here you can plug in 3 into each parentheses first, and then multiply the result. So that's going to be 3 squared minus 3 times 3 times 3 minus 2. So it turns out to be really nice, just 9 minus 3 is 6, 6 times 7. So 9 minus 2 is 7, 9 minus 3 is 6, 6 times 7 at the end. Right, so that's what could happen if you're given 2 functions or 3 functions. That you can either use them to use them in basic operations like subtraction, addition, multiplication, or you could find the conversational functions. All right. Now, the next thing I want to talk about is finding the domain of conversational functions. How do we find domain of conversational functions? So let's see, we want to find the domain of, let's say, f of g of x. Well, there are 2 things we have to be careful here. One is that we have to, first of all, we have to look at the inner function g of x. we have to decide, okay, which x value will make the g of x defined. So which x value we can put in the g of x and which one we cannot put in the g of x. So that's the first part. Find domain of the inner function g of x, because you need to make sure that g of x actually exists before we can take g of x put into a different function. And the step 2, so after we find the domain of inner function, what we have to do is we have to look at this f function at the end. So obviously, step 2, find the actual f of g of x, right? We need an expression for it. So that's going to be, let's say, f of some x at the end. I know it could be confusing, but when I show you an example, it's probably less confusing. So, let me erase this. So we're just going to find f of g of x. At the end, it's going to be a function of x. And then we have to make sure that whatever we found here at the end is defined. So that's a step 3, find domain of the new function. Now, we don't find domain of f of x that's given. We find the domain of this, like a new function, after we compose the two functions together. New function. And the step 4, we're just going to pick all the x values that will make both g and f of g of x defined. Find all x that are in both domains, domain of the inner function and the domain of the new function. Basically, where the two domains overlap. I'm going to use an example here. Hopefully that will help. Let's see, the example is, let's see, given f of x equals 1 over x minus 2, g of x equals square root x plus 4. So we're going to find the domain of f of g of x. So that's what we need. We need the domain of this new function, f of g of x. So the first thing I'm going to do is, you don't have to follow the order I did. You can just find the f of g of x first. It's up to you. So let's see, we can find, so step 1, find domain of the inner function, which is g of x. So we need a domain of square root of x plus 4. So the domain is going to be all the x values satisfying x plus 4 greater than or equal to 0. So x greater or equal to -2. So that's a domain. You can write as -2 to infinity. On the number line, it just goes from -2 here. The 0 is here. It's going from -2 all the way to positive infinity. -4. I'm sorry. -4. So the domain for g of x is from -4 to positive infinity. That's the domain of the inner function. And the step 2, what we're going to do is we're going to actually find the new function. So we don't look at the domain of f of x because that's not important at this point. So we're actually going to find the new function, f of g of x, which is f of g of x. Either notation is fine. So that's going to be taking the g function, put it into the f function. So that's going to be 1 over the x there becomes square root x plus 4. And then we still have a minus 2 outside. And in fact, I can drop the parentheses here because we have a square root. Okay, so this is the new function. I need to find the domain for this new function. Well, we have a fraction, so that I need to make sure that the denominator cannot equal to 0. Right? So let's see. So if I want the denominator is not 0, so that means square root of x plus 4 minus 2 cannot equal to 0. I'm going to move the 2 to the right-hand side, so we get square root of x plus 4 cannot equal to 2, even though it says inequality, but I can actually square both sides. I'm going to square both sides. So I get x plus 4 cannot equal to 2 squared, and x cannot equal to 2 squared, which is 4 minus 4, 0. So x cannot equal to 0, basically, at the end. So that's the domain for the new function. So domain of new function, it's going to be x cannot equal to 0. But remember that in this denominator, we still had this like a square root x plus 4, right? So you still need to make sure that this part is okay. So borrow what we had. That's going to be x greater or equal to negative 4 and x cannot equal to 0. That's the domain of the new function. But that's not the end of it. We have to double check, make sure that all the x values we pick is in the inner function, x greater or equal to negative 4, and also in this domain of the new function. Because anything we cannot have in the inner function, we cannot have it for the conversational functions, for the domain of conversational functions. So now if we think about it, so it's the domain of the inner function says, okay, x has to be greater or equal to negative 4. And the new function has a domain saying, okay, x has to be greater or equal to negative 4. So that doesn't really help. No new information there. So we still have x greater or equal to negative 4. But then we have to add a new condition, x cannot equal to 0. So this will be my domain of conversational functions. Now, you probably wonder, okay, how is this domain of conversational functions different from the domain of the new function that we found in step 2, right? I mean, in this case, they're the same, right? They're identical, but in some cases, they're not the same. You have to be very careful. In some cases, those two are not the same, so we still have to consider the domain of the new function and the domain of the inner function together to come up with the domain of the conversational functions at the end. So just because this example, they give us the same domain, it doesn't mean that always that case. All right, any questions on this? Okay. All right, the next thing we can do is we can take a function and decompose it into two functions. So decomposition of functions. For example, so given f of x equals 2 over 3 minus square root of 4 plus x squared. So we're going to write f of x as composition of two functions. So what that means is that, okay, we're going to find two functions that when we compose them, we get f of x. So what this means is find two functions whose composition is f of x. Oops. Okay, so how do we come up with two functions? Well, there's no restriction, so we can come up with any two functions. For example, the first function could be, let's see, we could just say, well, we have to replace the x with some expression, right? We could just say, okay, the first function, oops, the first function is going to be 2 over x. The second function is going to be the denominator. So example, the first set is going to be, let's see, g of x is equal to 2 over x, and the h of x is equal to 3 minus square root of 4 plus x squared. And if we take g of h of x, if we take h of x and put into the denominator, the g of x, to replace the x there, then we end up with f of x. So that works. But it doesn't have to be the entire denominator, maybe just a square root part that we can extract out as a new function. Or we can have, let's see, if we take the square root and treat it as a function, so h of x equals square root 4 plus x squared, and then g of x will be whatever we get after we remove this square root function. So that's going to be 2 over 3 minus x. So that also works. So g of h of x equals f of x. There are also other ways to decompose. Maybe we could take the x squared and treat it, as an inner function instead of square root of 4 plus x squared. Or we can treat 4 plus x squared as a function by itself, and whatever we get by extracting 4 plus x squared, the remaining could be another function. So decomposition of functions, you have a lot of options. It's a lot easier in some sense. But always double check at the end. Any questions about conversation and the decomposition of functions? Okay. If you don't have questions, the next thing I'm going to switch gear to transformation of functions. Transformations of functions. So you're probably saying those before a lot of times in the past. So transformation of functions, basically saying, okay, how can we, manipulate this function to get something else? We could, for example, we could shift it up, shift it down, left and right, stretch horizontally, shrink horizontally, stretch it vertically, flip horizontally. There's many ways. But I'm just going to write down the basic rule here. So suppose f of x is a parent function. So parent function means a function that's like the most basic function, like x squared, square root of x, 1 over x. Those are usually called the parent function. Let's see, for example, f of x equals x squared, f of x equals absolute value of x, etc. It's just the simplest function you get without adding a number or subtracting a number from the x or from the entire expression. So suppose f of x is a parent function, g of x is obtained from f of x through some transformation. Wait, what happened here? Okay. So through some transformations, And then we can write down a formula for g of x in terms of f of x. So we can write g of x in terms of f of x. I'm going to give you examples. For example, suppose, let's see, g of x is obtained by shifting f of x up by k units. So shift f of x up by k units. Then we can write g of x equals f of x, the function itself. When we shift it up, we only change the y value, right? We don't change the x value. So it's just the function itself adding a k. Now this could also be shifting downwards if k is negative. So up or down. If k is negative. But when we shift a function up or down, we usually add or subtract a number from f of x directly. And the second example would be shifting f of x left or maybe right by h units. Now, when we shift a function to the left, instead of subtracting a number from x, is that we actually add a number from x. So g of x will have the form of f of x plus h. So because we shift left and the right, we actually change the x value. So the change, the number we add or subtract, happens inside the parentheses where x is. So we add directly to the x, not to f of x. So note, so left, we have to add. But if we, let's see, shift it right by h units, then g of x will equal to f of x minus h. Now you probably think, okay, if we shift it right, doesn't right usually means positive? Don't we usually add? It is true, but when we talk about transformations, when we shift the graph to the right, we actually subtract. So right, subtract. Okay, so that's something to keep in mind. So it's opposite from what the operation suggests. If you think about positive being right, negative being left. All right, so that's this one. And the next one we can talk about is, let's see, reflection. So we can have a horizontal reflection. Now, when we say horizontal reflection, what we meant by that is we take a shape or function and then we reflect it over the x-axis. So over x-axis. And if we think about it, when we take a point, we reflect over the x-axis, the y value will become negative, right? The x doesn't change. So we can write g of x equals negative f of x, means that all the y value given by f of x is being multiplied by -1. And then the next thing we have is vertical reflection, which means we reflect vertically. Wait a minute, actually, you know what? Let me see, I might have confused those. Horizontal reflection, reflect horizontal. Oh my goodness, that's what I hate. All right, I might have to backtrack a little bit. Let me think. Vertical reflection, we reflect vertically. Oh my goodness. I apologize. When I said horizontal reflection over the x-axis and the g of x equals negative f of x, that's actually vertical reflection. Sorry.
It's all good.
Yeah. I always get confused with those. But for me, I always say, okay, let's just talk about reflecting over the x-axis or over the y-axis. So that's a vertical reflection. And the horizontal reflection is we reflect over the y-axis. And if we take a function and if we reflect over the y-axis, and if we think about it, any point we pick when we reflect over the y-axis, the y value stays the same, the x value will become the opposite because we go from a positive x to a negative x. So g of x will equal to f of the x value will be opposite, negative x. And then the last thing, well, there's a few more, but the next thing we're going to talk about is vertical stretch and compression. So if we take a shape, we stretch it vertically. Let's just say we have this. What that means is that we're just going to take every point and we stretch the y value of those points. So let's see if we stretch it by a factor of 2. So that y value will be doubled, this y value will be doubled, and this y value will be doubled. So it's become like more sort of like a skinnier. So g of x will equal to f of x times a constant. Let's see, the constant could be a. If a is positive, well, a usually is positive when we talk about vertical stretch and the compression alone. If a is negative, it's just going to be a vertical stretch plus a reflection. If a is more than if a is between 0 and 1, that's just going to be a compression because we kind of like compress all the y values. 6, we're going to talk about horizontal stretch. Now we have to be a little bit more careful when we talk about horizontal stretch. Let's say if we stretch horizontally by b units, it's not like the actual graph will be stretched. All the x values will be multiplied by a factor. But when we write down the formula for g of x, it's actually f of, so horizontal stretch by b is actually f of 1 over b times x. Actually, the reciprocal that's in the formula. And similarly, horizontal compression by, let's say, by 1/2, for example, 1 over b. Suppose b is more than 1. So if we compress by 1 over b, then the formula will be g of x equals f of the reciprocal of 1 over b, so b times x. So just one thing to remember that with horizontal transformations, it's always kind of like an opposite from what we want to believe. If we stretch by a factor of 2, we actually multiply by 1/2 in the formula. If we compress by 1/2, we actually end up multiplying by 2. So it's always a reciprocal of what the factor says. So reciprocal. So be careful there. Just like when we shift it left and right, it's not adding a number to move it to right. It's actually subtracting a number when we shift it to the right. All right, with that said, let's look at some example here. Let's see, I have one example, my graph. So here's the graph. And what we're going to do is we're going to perform a few transformations. So consider f of x is given. So this is what we call f of x. And we're going to graph g of x, which is equal to, let's see, negative 2, I don't want to do negative 2, just 2f of x plus 1, and then minus 1. Hopefully we have enough points on the grid. Yeah. All right, so that's a formula for g of x, and it's obtained by transforming f of x, right? We have to look at what kind of transformation are happening. So we can either look at the x direction, which is inside the parentheses. So all the x transformations are inside the parentheses. It says x plus 1. So that tells us this is going to be, so x direction. That's going to be just one transformation, right? Plus 1 means shifting left by 1 unit. Okay, so let's do that. So if we take this graph, we shift it left by 1 unit, so all the y values stay the same, but x being moved left by 1. So this point goes there. This point will go here. This point goes here, and that point goes to 6. So we kind of have this curve, and then straight line, and then straight line. So that's shifting left by 1. And now we're going to look at the y direction. So now in the y direction, so this is my y value, right? F of whatever. And this y value is being multiplied by 2. So y direction. So it's being multiplied by 2. So we have to consider that first. So that's going to be a multiplied by 2. That's a vertical stretch by 2. So we're going to take all the y values of each point. We're going to multiply by 2. So this point is negative 1, 1. So that becomes negative 1, 2 when we multiply by 2. This one is 2, 3. 2, 3. So that becomes 2, 6. And this point is 5, 2. So it becomes 5, 4 when we multiply the y value by 2. And this is a 6, 0. Well, if we take 6, 0, we multiply the y by 2, it's still going to be 0. So this point stays. It doesn't move anywhere. So if we draw it nicely, this is the curve. That's a straight line. And this is also a straight line. So that's a vertical stretch by 2. All right. And then the last thing we have to do here, after we multiply by 2, we have to subtract 1 following order of operation, right? So the last one is going to be down 1 unit. So if we shift it down by 1 unit, so take this point, we move it down, so it ends up here. And take this point, we move it down 1 unit, it's become here. And that one becomes there. And then the 6, 0 becomes 6, negative 1. So we end up with this shape, the green one. Green color. So at the end, this is g of x. Any questions about transformations? Okay. Now, just want to point out that when we, just in this case, in the y direction, we have multiple transformation going on, right? We have this vertical stretch, and then we have this down unit, minus 1. So over there, you just look at which one first. So you follow the order of operation, which says we're going to take the f, we're going to multiply by 2 first, and then we subtract 1. So if you follow that order of operation, you're not going to get it wrong. But I want to expand it a little bit. So for y direction, follow order of operation when we have multiple transformations. So if it's multiply first, I mean, that's what we do. If we, so this one is let's see, 2f x plus 1 minus 1. So this means we're going to do the stretch first. Then we're going to do the shift down. But if I write it as 2 bracket f of x plus 1 minus 1, for example. Now, the bracket says we're going to perform whatever inside first. So that's going to be down 1 unit first, and then we're going to stretch. So that's a vertical in the y direction. You have to be careful with the parentheses. If there's no parentheses, you just do the multiplication, then add addition, subtraction. Right. But for x direction, it's a little bit different. So we don't follow the order of operation. We follow the opposite of what the order operation says. Follow opposite of order of operation, the reverse process. Now, what I meant by that, I'm going to give you an example here. So let's see, we have f of, let's see, 2x plus 1. Right. So normally, if you think about, okay, x is being multiplied by 2 first and then adding 1 to it, right? You probably think, okay, I'm going to do the horizontal compression first because it's multiplied by 2, and then do the shifting to the left. But no, actually, everything is the opposite. So this one says we're going to think about the plus 1. So the plus 1 says we're going to shift left by 1 first. And then we're actually going to do the multiplication, multiply by 2. Then we're going to multiply by 2, which says it's going to be horizontal compression, not stretch. By 1/2. So that's something I want to point out. It's not as straightforward as what the expression will suggest. You have to think in terms of the reverse order, not the order of operation. Another example, if I have f of, let's see, parentheses 2, so f of 2, so f parentheses 2 parentheses, let's see, x plus 1. If it's written in this way, you probably think, okay, we have to do the parentheses first, x plus 1, and then we have to multiply by 2. No, we actually do the opposite. We do the multiplication and then the parentheses. So in this case, first, what we're going to do is we're going to think about the multiply by 2, which is saying that we're going to do a horizontal compression by 1/2. And then we're going to look into the parentheses, see what happened inside the parentheses. Then we're going to look at the parentheses, which says we're going to shift left by 1. That could be really confusing if you're not familiar with this type of examples, but I just want to point this out. This is something we should pay attention to when we look at transformations. With the y, with the y direction changes, it just follow whatever the operation says, whatever the operation the operation suggests. Like, if you multiply by a number, you vertically stretch. If you add a number, you shift it up. Subtract, you shift it down. But with x direction, you have to think in terms of like the backwards, the inverse of what's happening. All right. So let me give you one example. So suppose g of x is obtained from f of x through the following transformations. So the transformation says we're going to shift f of x up by 5 units, then horizontally stretch by a factor of 2. Then vertically vertically flip over x-axis always. Then at the end, we're going to do vertical stretch. Let's see vertical compression. By 1/3. So write a formula for f of x. So write a formula, for g of x. Formula for g of x in terms of f of x. So here we have f of x. We're going to shift it up by 5, and then we're going to horizontally stretch it by a factor of 2. Then we're going to vertically flip that whatever we get over x-axis, and then we're going to vertically compress the result by 1/3. So whatever we get, that will be g of x. But can we write down a formula for g of x in terms of f of x? So this is what we're going to do. We're just going to follow the steps one at a time. So we know that g of x is going to be some expression with f of x. So let's see what happened to f of x first. So we're going to shift it up by 5. So if we shift it up, we add a number to the f parentheses, right? The entire expression, we're going to add a number to it. So we're going to add to this f of x, we're going to add 5. That's shifting it up by 5. And then we're going to stretch it by a factor of 2 horizontally. Well, if we stretch it, if we stretch horizontally, that's only going to affect the x value. It doesn't affect the y. So horizontal stretch by a factor of 2. Remember, if we stretch by 2, is actually the reciprocal multiplied by x. So it's going to be 1/2 times x. So that's a horizontal stretch by 2. It's x times 1/2. And then it says we're going to flip over the x-axis. It's a vertical flip. Now you have to be careful. A vertical flip is not, in this case, it's not simply just a negative in front of the y, because we have to add the negative in front of this expression. Because that's what we get, f of 1/2 x plus 5. We're going to take that function, we're going to flip vertically. So it's a negative of the entire expression. And then we're going to vertically compress by 1/3. What we're going to do is we're going to take whatever we have, we're going to multiply by 1/3. Now you probably think, okay, this multiply by -1 and this multiply by 1/3. Can we somehow bring them together? Yes. So if we have a vertical stretch and a vertical flip, it doesn't matter which one goes first. We can rewrite it as -1/3. But then we still have this f of 1/2 x plus 5 in the bracket. So this is the correct way to write it at the end. Now you probably think, okay, can I distribute the -1/3 into each term? That's fine. It's just that we sometimes prefer to leave it this way because this kind of reflects what's actually happening. If we distribute the -1/3 in there, we get -1/3 f of 1/2 x plus minus 5/3. So it's difficult to kind of get the exact transformation from this distributed form. All right, any questions about what I did over here? No? Okay. All right. With that said, let's see. I think we're pretty good. Let's take a quick break. Let's see, it's 7:17. Let's see, 7:25. All right, let's come back at 7:25, and then we're going to finish one more section. That should be good for today. All right, welcome back. So I'm just going to finish the next section. But before I do that, I want to give you another example quickly with transformations. I just want to show you with horizontal transformations, if you have multiple things going on, how do you write down the formula? So let's see. Suppose g of x is obtained from f of x from f of x. Let's see the transformations are through first a horizontal shift to the right by 5 units, then a horizontal compression of a factor of 4. So suppose that's the transformation that's happening to f of x. So how do we write down the formula for g of x? So g of x is equal to, so since those both transformations are horizontal, so we're not going to worry about anything in front of f part. So it's just going to be inside the parentheses. But the first thing it says, okay, we're going to have a horizontal shift to the right by 5. So when we shift it to the right side by 5, it's not adding 5 to the x, it's actually subtracting 5 from x. So it's going to be x minus 5. That's a horizontal shift to the right. And then it says we're going to have a horizontal compression of a factor of 4. And if you remember, sorry, I should say it correctly. Horizontal compression of a factor of 1/4. Now, if we compress it by 1/4, it doesn't mean that we're going to take the x multiplied by 1/4. We actually multiply by the reciprocal of 1/4. So it would be 4 times x. So 4 times x will be the horizontal compression. But then you have to check, make sure that the order is correct, that we have a shift first and then a compression. So which involves the opposite of order of operation. So normally it says, okay, we're going to multiply by 4 and then subtract 5. But here we have to do the opposite. We're going to subtract 5 first and then multiply by 4, which is correct, right? We're going to subtract 5, that gives us a horizontal shift. And then we're going to do the horizontal compression, which is multiply by 4. So that's a correct way to put it. All right. Any questions, or should we do another example on this? All right, if you want me to do another example with horizontal transformations, please let me know. So just think about that. Horizontally is, you kind of have to think like it's the opposite of what's happening. Hopefully we're not going to see a lot of horizontal transformations, but you have to know, like, you have to know, what it means to shift it right, what it means to stretch horizontally by a factor of 5 or 10. Okay. All right. So the next thing I'm going to talk about is 1.6 absolute value functions. Now, the parent function for absolute value functions is just going to be f of x equals absolute value of x. And you all know what the shape looks like. It looks like a V. And it goes through the origin, has a slope 1. It's basically like a 2 arrays joining together at the origin. So that's the graph for absolute value of x. And if we convert it to piecewise functions, it has 2 pieces. The first piece is going to be positive x if x is greater or equal to 0. So the first piece is this part. So that's positive x for x greater or equal to 0. Now the piece on the left will have a function negative x. Now it's on the left, it's negative x. It's not because it's on the left, it's because x is negative in this case. Now, if you think about it, so here x is negative, so this part, this x is negative. And if we take a -1 multiplied by a negative number, we actually end up with positive. So together, let me use a different color here. So together, negative x actually is positive because x itself is negative, right? And which is good that negative x means positive, which is a good thing because that's what the definition of absolute value of x is. It's always positive if you take an absolute value of any number. So there's no contradiction there, even though there's a negative sign, but the negative actually is helping to make a x value positive, make the x positive. Okay. And a general formula of a absolute value function has the form of f of x equals a, well, sometimes they write m, means the slope, m times absolute value x minus h, absolute value plus a k. So you can think about this as a transformation from f of x. So this means if we shift the absolute value of x to the right by h, and then up by k, and then we perform a vertical stretch, and it could be compression, depends on the value for each. But if suppose m is positive, h is positive, k is positive, so that's what it is, and m is more than 1. So that's a general formula in terms of transformations. But you can also think about this m. It's just the slope of each line. So the slope of the line on the right will have a slope m, and the slope on the line on the left is going to have a negative m as a slope. So that's that. Let's see. What's next? All right, we can graph some absolute value functions. So example, graph the following function f of x equals 2 absolute value x minus 3 minus 4 using transformations. Let's see, I'm going to change the paper to grids. So to graph it using transformation means that we're going to use transformations from y equals absolute value of x. So suppose I begin with this absolute value of x graph. Oops. So this is a y equals absolute value of x. And what can we do to transform it to get f of x? Well, the formula says the first thing we're going to do to the x is we're going to subtract 3. Well, when we subtract 3 from the x, so x direction, it's actually we're going to shift it to the right by 3. So that's what x minus 3 says. So we're going to shift it to the right. So I'm going to take this point, shift it to the right, 1, 2, 3. And we're going to take this point, shift it right by 3, 1, 2, 3. And then this point, 1, 2, 3. So we get those 3 points. And then we're just going to draw arrows, go through them. So that's shifting to the right by 3. So that's give us absolute value of x minus 3. And then what we're going to do is we're going to look at what happened to this absolute value of x minus 3. We're going to multiply by 2. Now, if we multiply by 2, And that tells us in the y direction, when we multiply by 2, it's going to be a vertical stretch. By 2. So all the y values, we're going to multiply by 2. But the point on the x-axis, that doesn't go anywhere when we multiply the y by 2, because 0 times 2 is 0. But the point on the left, it's going to go up because that's 2, 1, so that becomes 2, 2. And the point on the right, again, that's the 4, 1, that's going to be 4, 2. So we end up with this graph. So this new one, this is 2 times the absolute value of x minus 3. And then the last thing we have to do is the negative 4. So the negative 4 tells us it's going to be down 4 units. So if we take this point on the x-axis, move it down 4 units, 1, 2, 3, 4. Give us this point, the point on the right, this point, 1, 2, 3, 4. This point on the left, 1, 2, 3, 4. So we get this point here. So now we have 3 points. We can just draw the arrow here. So this is the f of x equals 2 absolute value x minus 3 minus 4 at the end. Any questions? Does that make sense? All right, let me know if you have any questions. I imagine that you all seen it in the past, but for some of you, it probably have been, been a while. Right. Now, next question I'm going to give you is similar to the transformation questions. So basically, we have a function that's obtained from absolute value of x through the following transformations. We need to write down a formula. So let's see. Let's see. The graph of f of x equals absolute value of x is being shifted horizontally to the left by 2 units. By 2 units. Then whatever we get is going to be vertically flipped. And after the vertical flip, and there's a vertical shift vertically shifted up 3 units. So whatever the function we get at the end, we want to express it in terms of absolute value of x after those transformations. So write a formula for the new function. Okay, so what we know is that we take the absolute value of x, f of x equals the absolute value of x function. We're going to shift it horizontally to the left by 2 units. And then we're going to vertically flip the result. And at the end, we're going to vertically shift up by 3. So let's write this. The new function, you can call it f of x or you can call it g of x. It doesn't matter. I'm going to call it g of x. And the horizontal shift to the left only going to affect the x. It doesn't affect anything outside of the absolute value. So that's going to be affecting this x. If it's to the left by 2, it's actually x plus 2, not minus 2, x plus 2. So that's left by 2. And then flipped vertically, if we flip vertically, it's going to be, sort of the y, in this case, the entire expression, absolute value x plus 2, that's going to multiply by -1. So just put a -1 in front of this absolute value. You can just put a negative sign, don't have to put a 1 there. So it's a negative absolute value x plus 2. And at the end, we're going to shift up vertically by 3. When we shift it up by 3, that's going to be taking whatever we have and all the expression there, because those are the y, and we're going to add 3 to shift it up by 3. And that will be the formula for the new function, new graph we get. Any questions? All right, we are almost done here. We have a few things to do, and that shouldn't take too long. Hopefully we can finish by 8. All right, so the next thing we're going to do is we're going to find the zero of the zeros of the x-intercepts of a absolute value function, just for practice. So I'm going to take the example above. So find x-intercepts, all zeros in this case, of f of x equals 2 absolute value x minus 3 minus 4. So how do we find x-intercepts of a absolute value function? Well, it doesn't matter what function it is, right? If it's the x-intercept of zeros we're looking for, so that means the y has to equal 0. So we're going to set f of x equals 0. So we get 0 equals 2 absolute value x minus 3 minus 4. So that's a starting point. Okay, so how do we solve this? We could plus 4 on both sides, divide by 2. That's perfectly fine. So let's see. I'm going to add 4 to both sides. So we get, or we can just move this expression to the left completely. But that's going to create a -2. So I'm going to add 4 to both sides. So I get 4 equals 2 absolute value x minus 3. And then I'm going to divide by 2. So 4 divided by 2 is 2. So 2 equals absolute value x minus 3. Well, what do we do next? Now, if you remember with absolute value equations in the past, every time you have absolute value equation, you're going to have to write down 2 equations. The first one is keep exactly the same form. So 2 equals x minus 3. And the second one we're going to write is actually adding a negative sign in front of whatever is inside the absolute value. So it'll be 2 equals negative. So it'll be negative. And then whatever inside the absolute value stay the same, x minus 3. So there's an extra negative here in the second equation. And from here, we can solve for x by adding 3 to both sides on the left. So plus 3, so we get x equals 5. That's 1x value. And the expression on the right, we have to either divide by negative or distribute it first. It's up to you. So I'm going to divide by negative. So we get -2 equals x minus 3. Then we're going to add 3 to both sides. So we get x equals 1. So here we have 2 x values that are x-intercepts or the zeros of the function. But I just want to emphasize that this is the important part. So whenever you want to look for the x value in this absolute value equation, you have to write down 2 equations. Another thing I want to show you quickly here is that you don't have to wait until this step to write down 2 equations. You can write down 2 equations from the beginning. So the first equation we can write, it's just going to be exactly the way it is. So 0 equals 2. Instead of using absolute value, we're going to use parentheses, x minus 3 minus 4. That's the first equation. The second equation we can write is we're going to add a negative in front of the absolute value part. So 0 equals 2 times -1 times x minus 3. because x minus 3 is the absolute value part. We're going to take that, multiply by -1, and then everything stays the same. So that's the second equation we can write. And if you solve both equations correctly, you should end up with 5 and a 1, just like before. So 2 equations. The first one, you can just think about it as being multiplied by 1, so there's no negative there. The second equation is the absolute value part being multiplied by -1. Everything else stays the same. Any questions? Okay. All right, let me know if you have any questions. So let's work on another example, which is solving absolute value inequalities. So here I have an example here. To solve absolute value x minus 2, let's see, greater than 6. Okay, so we can either look from the graph, we can look at it, or we could just try to solve it. Again, just like before, if we have absolute value inequality, we're going to write down 2 equations. The first one is going to be exactly the way it looks. So x minus 2 greater than 6. That's the first equation. Or we can write down the second equation, which is going to be the absolute value part will be multiplied by negative. So x minus 2 will be multiplied by negative, and then greater than 6. So everything stays the same. We don't flip the sign yet. We're just going to add a negative in front of the absolute value expression. So this is the negative right here. Then we solve each inequality separately. So we get +2 on both sides with the inequality on the left. So we get x greater than 8. Or we can have this one, we have a negative, so it's probably better to get rid of the negative first. So remember that when we add or subtract, when we multiply or divide by a negative, we flip the sign, flips the direction of the inequality when multiply or divide by negative. So I'm going to divide by -1 first. So we get x minus 2 is still there. And the divide by -1s are to flip the direction. And the 6 divided by -1 is -6. Then I'm going to add 2. So I get x is less than -4. So at the end, we have either x is going to be greater than 8 or x is less than -4. And if we look at the solution on the number line, that's going to be greater than 8 is here. It's greater than 8, so it does not including 8. So we put a circle there. And the less than -4, let's see, -4 is here, 0 is here. -4 less than -4. So again, it's going to be a circle because we don't include -4. So that's the sort of like the graphical representation of the solution. Any questions? Okay, awesome. All right, let's do one more example, then we can just call it the end of the lecture. So the next example I have, again, we're going to solve this absolute value inequality. -2 absolute value, let's see, k minus 4. Oh, I apologize. I do have another example to go over, but it shouldn't take very long. Less than or equal to -6. Okay, so what do we do with this? Well, there's 2 things. One is that we can directly write down 2 equations from here. One is with the part exactly what it looks like with the absolute value. So I'm going to show you the first method. Method 1. So write 2 equations, 2 inequalities. So the first one is going to be -2 times k minus 4 less than or equal to -6. The second inequality is going to be -2 times, we're going to have to add a -1 in front of this absolute value part, k minus 4 less than or equal to -6. And then we can do whatever we have to do. So that's the first thing, the first method. If you don't like this, we can go with the second method, which is we can simplify everything. We can simplify the -2 first by dividing by -2 on both sides. So divide by -2 to get just kind of clear everything on the left side. So divide by -2, so we get k minus 4 absolute value. When we divide by a number, we have to flip the direction. So greater or equal to -6 over -2, which is going to be 3. And from here, we don't have a choice. We have to write down two equations, two inequalities. Then write two inequalities. So the first one is going to be k minus 4 greater or equal to 3, or negative k minus 4. So again, we have an absolute value we need to get rid of. We have to have positive and negative. So -1 times k minus 4 greater or equal to 3. We don't change the direction there until later. And now we can solve the first one by adding 4 to both sides. So we get k greater or equal to 7. Or we can have the second one when we solve, we have to get rid of the negative. So k minus 4 less than or equal to -3, adding 4 to both sides. So we get k less or equal to 1. So at the end, if we want to graph the solution on the number line, so we get k is greater or equal to 7. So let's say 7 is here. It's greater or equal to 7, including 7 that we're going to actually put a dot there, not a circle. So from 7 to the right. And then k less than or equal to 1, again, including 1. So this is a 1. So we're just going to go left. This is 0. So in this case, both parts of the solution, including the boundary value. So we're going to put actual points on the number line. All right, let me know if you have any questions. I mean, like I said earlier, this more or less looks like a review. So the last thing I'm going to talk about here is using absolute value expression to describe points that within a certain distance of a number. So use absolute value expression to describe all x values that are 5 units from 17, for example. So here's 17. And we want to describe all the x values that are within 5 units that are, within 5 units from 17, including 5 units. So we could go this point, and at most, it's going to be within 5 units from 17. And then we could also go left, but at most, we could go 5 units from 17 on the left. So how do we, using the absolute value expression to describe all those points? It could be infinitely many points, right? So to describe it, we're going to use the distance idea, because let's see x is here. So the distance between x and the 17 is going to be less than or equal to 5 for x on the left side. Or if we think about x is on the right, let's say x is here, the distance between x and 17 is less than or equal to 5 again. Doesn't matter which side x is on, the distance between x and 17 is always less than or equal to 5. So we're going to write x minus 17 means the distance between x and 17. Whether it's on the left or right, we're going to put the absolute value to kind of get rid of the negative distance. And that value, this distance, so this means distance from 17. So this distance must be less than or equal to 5 in order to be within the 5 units. So that's the absolute value expression to describe the distance from a given point, given value. So whenever you have this kind of problems, just think about distance. All right, any questions on what I talk about today? I know it's like a relatively fast the way I went through this because again, this is the material from chapter 1. I'm pretty confident that you saw most of it, if not all of it, from previous classes. That's not my excuse to go through fast. It's just really not a lot of complex concepts here. So on that note, if you don't have any questions, I'm going to let you go. So I'll see you on Wednesday. Remember, there's a quiz. The homework will be available later today or early tomorrow morning, but you have until Sunday. All right, take care, everyone. Okay, see you.
Thank you.
Yep, no problem. Bye-bye.
Thanks. Have a good night.
Yep, take care. Let's see.
Hey, can you hear me?
Oh yeah, hi Ethan. Yeah, we're supposed to talk, right? Do you have a minute?
Yeah, I got some time.
Awesome. All right. William, do you have any questions? All right, we still have William here, but that's okay. Ethan, I'm going to put you in a breakout room, and I'll be there in a minute.
Okay.